You want to?
It's a pleasure to have a seminar today by Professor Lance Dixon at Stanford and SLAC. I think SLAC is a department at Stanford, right?
Yeah.
He has given so many contributions to theoretical physics. I think that was it the first orbifold? The very introduction to orbifolds in string theory. Paper by Lance, and then he had many other contributions to string theory. And string theory was, I think, maybe a motivation to go into amplitudes, where the first results were obtained by taking some limits of string amplitudes, and then more and more powerful methods were developed. Lance was one of the leaders in these developments, and today he will talk about bootstrapping amplitudes in planar N=4 superimmense theory.
Thanks a lot for that very nice introduction, Massimo. It's a real pleasure to give a talk where I can actually see the audience and to meet with people in multiple days at another institution. It's been a while. And yeah, I moved from amplitudes to from string theory towards amplitudes in the early 90s. And I think the last time I was at NYU physics, Glennis invited me to come, and I was talking about next to leading order corrections to or jet production and E plus and minus colliders. So that was a while ago. And so some of this material of scattering in this other theory, planar N=4, was kind of an outgrowth, or we were using it as a way to try to see how to organize QCD amplitudes. But later on, it's taken a life of its own. And we can do things in this theory that we can still only imagine doing in QCD. So I wanted to tell you something about that. Let's see if I can figure out how to advance. Use the mouse. So it's this one here?
Yeah, just the arrow.
Okay. Yeah, thanks. So, I mean, there are a lot of uses of the term bootstrap. For example, there's the general conformal bootstrap program. There's even an S-matrix bootstrap program, and they're all a little bit different in emphasis. So this particular bootstrap that I'm talking about is where we pick a specific theory, and we're entirely going to be talking about planar N=4 super-Yang mills, which I'll define a little bit later in this talk. We're going to try to explore its non-trivial scattering amplitudes for processes which are simple but not too simple, by making some assumptions about their functional dependence. That is, they're analytic functions of some type. And if we can guess what they are, we can then guess that the answer is just a linear combination of those functions. And if our guess has few enough parameters, we could constrain them all by using some known or maybe suspected properties until everything's uniquely determined. And then if we have additional properties that we haven't used, to fix all the coefficients, we can use them to cross-check everything and convince ourselves we got the right answer. And then once we have the right answer, turns out that's not really quite the end of the story, because the way we represent the answer in very high loop orders is really nested. It's like these Matryoshka dolls. You have to unpack the whole thing in a particular region in order to get numbers out of it. And that's the sort of general framework we're going to follow. This is just a teaser of one result we can get. This is a six-gluon scattering in this theory. And the core finite piece of the answer depends on three variables, but to plot it, I made all three variables the same. And I just normalized them at one point, so to make all the curves sort of normalize the same. And these are just the coefficients of this function. The one loop one turns out to be identically 0 for this convention, but you can plot the ones from 2 to 7 loops. And like down here, they're all basically proportional to each other to very high accuracy. And then at larger values of this variable, they fan out. But you can see they're fairly predictable if you you can probably guess where the 8 loop one would go there. The high accuracy. So there's a lot of regularity in the structure. I'll come back to some of that at the end.
AGN means.
Oh yeah, this guy can be predicted at very strong coupling too, where you're minimizing the area of a certain hexagon. And this one's so symmetric that it can be done analytically. So there's a simple analytic formula for the very strong coupling coefficient, as well as formulas that look very different for the weak coupling coefficients, but numerically they're very proportional.
So wait, can I just be totally clear on what's being played here? This is each individual amplitude, or this is the sum
Yeah,
as
it's
you
not,
have?
it's not the partial sum. It's
each
individual
amplitude.
coefficients, partly because we don't know what the coupling is, so we don't know how to do it. Or we could do a partial sum for different couplings, but because the coupling is variable, and it's a nice theory for any value of coupling, we're just I'm plotting the individual loop order coefficients. Later on, I'll show you some plots that are a little different, or plot the ratio of successive loop order coefficients, which is a little more instructive for what the growth of perturbation theory is, what its behavior is, whether it's factorial or power loss.
Apologize, I ran down to get a door shut to reduce the background. So I missed, U is just like a Mandelstam variable.
U is like a ratio of 2 Mandelstam variables over 2 other Mandelstam variables. But
And
it's,
you
yeah,
pick some value of the.
it's
coupling.
some kinematic quantity associated with the energies and scattering angles. But this theory, the answers depend on pure kinematic variables, as we'll see. So it's only particular special ratios of Mandelstam variables that are important.
Lance, I
Yeah.
mean, this is the context of planar, so it's integrable and you cannot create particles, so it's a 3 to 3. It will correspond to 3 to 3 scattering amplitude.
Well, the theory is integrable in the sense of a 2-dimensional surfaces. But it doesn't obey the kinds of integrability restrictions that lead to a trivial particle production. This theory has particle production at the level of gluons. So it can be 2 to 4 or 3 to 3. Now this is actually plotted in the unphysical Euclidean region, so it's neither. But you can also make plots in physical regions. Any other questions? So basically, we can get to very high orders, like 7 loops in that example. I'll show you another case where we can get to 8 loops, and we have one other 4-loop example. And it's pretty rare in perturbative quantum field theory to have high loop order results that are simultaneously functions of multiple variables. And by playing with those variables, you can go into interesting kinematic regions where the amplitudes factorize in different ways. Like for this 6-gluon amplitude, we have like at least 3 or 4 distinct kinematic regions. Some of those, we use some of the data to fix the answer, but then some of them are like pure predictions. So you can use all that. And here's just a sketch of like 3 possible ways you might consider doing a perturbative calculation. One would be to draw the Feynman rules, Feynman graphs, and use the Feynman rules to construct a formula for the transition amplitude. And at the loop level, there are still loop momenta in the diagram that you would have to integrate over. Often with computer algebra, the last step is the hardest one, the performing the loop integrations. But can often be done. There's also a possibility of assembling the loop integrand in a different way from information about the unitarity cuts. And in many cases, that's more efficient than doing individual Feynman graphs. You sort of assemble the whole thing at once, but you still get an integrand, a function of the loop momenta that you have to integrate over. But another strategy would be to just guess what all the integrals look like, and then write down the answer as a linear combination of known functions, as I was saying earlier, where there are unknown constants in front of them, which will always turn out, in our case, to be over the rational numbers. And so we'll be solving constraints on these amplitudes and various limits that give us linear equations in these unknowns. And if we have enough equations, then it's just a problem of linear algebra. I mean, in some cases, we could have a few 100,000 equations in 100,000 unknowns, but it's still just linear algebra. Sometimes you need to use specialized techniques to get the solution out, but it's straightforward. And then once you have it, you get the answer. It's assembled in a different way. This might be expressed in terms of the contributions of individual diagrams. This in terms of different types of integrals that you might see at the integrand level. And then this will be, in the cases where we can do it, these functions are all drawn from a very uniform space, which I'll start describing to you in a little bit. This is the massless spectrum of n equals 4 super Yang-Mills theory, first written down in the 70s by these folks. It has a massless spin 1 gluon that has non-abelian Yang-Mills interactions, just like QCD gluons. But the matter is a little different. It has 4 different massless spin 1/2 gluinos and 6 massless spin 0 scalars. And it's all in the biggest supermultiplet you can make with it having maximum spin of 1. So this is the sort of, if you have spin greater than 1, you get spin 3/2. We don't really know how to make a good theory of that without spin 2, that is supergravity. So this is the biggest supersymmetry you can have without bringing gravity into the game and just flat space-time. And because of supersymmetry, all these particles are in the same representation, the adjoint representation of the gauge group. And the number of states here just reflects the 4 supercharges, and then 4 choose 2 is the number of ways of taking 2 supercharges that anti-commute together, and then you get 4 choose 3 or 4, and then 1 at the end. And the gauge group is usually often in this game taken to be SUNC for a number of colors. We can compare QCD and n equals 4 super Yang-Mills, and a lot of the Feynman rules are rather similar. This non-abelian gauge vertex is identical. They're in some sense the same gluons, but in QCD they're coupling to a certain number of flavors of quarks in the fundamental representation. And here are adjoint, which is represented by this double color line. But you can see it's not, it's kinematically, it's the same coefficient. So you can kind of deal with the color bookkeeping the right way. These quarks and gluinos often look fairly similar. But then there are also some scalars that couple to the gluons and also have scalar Yukawa interactions with fermions and so on. So that's what you would get sort of out of the Lagrangian. In fact, at tree level, if you were just doing multi-gluon amplitudes, because these vertices are the same, and because the matter can only be pair produced, the n-gluon amplitude is simultaneously amplitude in QCD and the amplitude in n equals 4 super Yang-Mills. So these tree gluon amplitudes have been known for a long time, that they obey all the symmetry identities or word identities you could derive from n equals 4 supersymmetry. One such identity is that if all the gluons are right-handed, like plus felicity, or if one of them's opposite-handedness, you always get 0. That's a consequence of supersymmetry. Even if you have 2 negative felicities, or you get something at tree level called the Park-Taylor amplitude, it's essentially independent of the location of those negative felicities due to some word identities of supersymmetry, which allow you to move around where the negative felicity is. So QCD at tree level has loads of special features because of its kind of coinciding with n equals 4 at that order. But we're going to go to the loop level. Any questions about that though?
I'm confused about the second top loop thing. I mean, if I think of like a four-gluon scattering, I can put a fermion loop. That's not what you're trying to say.
I said this is a tree amplitude.
Right, you say
so-
fermion's a scalar.
So if you have just a tree amplitude of gluons, yeah,
Of course.
it's the same in both theories. Yeah, you know it very well.
Number five.
And it's just at the loop level, they start to differ.
No, but it's a triviality at tree level.
It's a triviality, yeah. That's all I was saying.
It's not like you can't have fermions in a tree level amplitude or anything.
Right, so you could ask, what happens if I have a bunch of gluons and then one fermion line? So even that one, there will be a non-vanishing amplitude, but it will actually be the same except for color as the one in n equals 1 or n equals 4 with one of the gluinos replacing the quark. The only difference is the extra color, and that's easy to deal with. So the amplitudes in QCD with quarks in them can also be related to the ones in gluons through Susie Ward identities, which hold at tree level. And then those start to get violated at the loop level. So, yep, at the loop level, you see different things when you compare n equals 4 and a random gauge theory. In n equals 4 case, there's a lot of cancellation in the loop momenta, so that you don't get very large powers of the loop momentum in the numerator. It's roughly related to why Susie kind of solves the hierarchy problem. It has better ultraviolet behavior. But n equals 4 has such good ultraviolet behavior that the only integrals you ever see at one loop are what we call scalar box integrals. So integrals with 4 propagators for the scalars multiplying each other that you then integrate over. And this integral, if these were like momentum P1, P2, and P3 recoiling against something else, turns out to have this form. So it has the dilogarithm in it, which I'll define on the next slide, and also squares of logarithms. But this thing is more complicated than the other kinds of integrals you can get and do get in QCD, but not in n equals 4. You also get triangles and bubble integrals. And those are basically simpler and kind of just involve single logarithms.
What do you mean by a weight 2 function?
Yeah, I'll define that on the next slide. Sorry. So the weight is defined to be the number of integrations of some rational d log type form. So the logarithm is the integral of the d logarithm, or dt over t, from some base point to another point s. So that's a single logarithm. And the dilogarithm is defined by integrating a suitable logarithm dt over t. So it has a d log t of something that was also a d log. So that's 2 integrations. So we assign that weight 2. And then there are other higher polylogarithms that you can define by continuing to integrate dt over t of the n-1 dialog. So you can define a class of functions that have weight n there. This is not a big enough class of functions for the thing we need, but it's an example of what functions of different weight are. Also notice that if I take the derivative of this guy, I get this one times the d log times 1 over x, the differential of log x. We'll see that come up again in more generalities. Now, the amazing thing is that when you look at these answers in n equals 4 super Yang-Mills theory, they always have uniform weight. At L loops, you always see only things with weight 2 equal to twice the loop order. So that's a generalization of the fact that those box integrals at one loop had weight 2, having dialogues. At weight 4, at 2 loops, you have tetralogs and so on. So we're going to be able to make it to 8 loops, or whatever 16 is in Greek logs by the end.
So, and this weight is not obtained by taking products of lower functions. So
yeah, in general, there are things in that weight that are obtained by taking products, but those are in some sense more trivial. And there's a much richer, larger class of functions that are they're nested path-ordered integrals. So you keep integrating, and if I plugged in this definition, you would see that I get a path-ordered integral. That's sort of the general property. Yep.
Sorry, I have a very naive question. So here you mean you only have weight 2 errors, you mean lower weight diagonal.
That's right.
Cancel.
It all cancels out exactly. In the QCD case, you get a whole bunch of lower transcendental debris, I would call it, but it plays an important role physically. But the maximum you get in both cases is 2L. And in the n equals 4 case, you only seem to get 2L. What?
What is behind this property? Is it maximal supersymmetry? You have it also.
Well, you can say that since it's observed in n equals 4, and that is maximal supersymmetry. You can also, you can prove it in one loop, and then you have other arguments based on another symmetry, dual conformal symmetry that restricts some of it, but the full statement is still somewhat empirical, but it always works. Since it always works, we build it into our assumptions. And that was for an arbitrary gauge group. The next step is to take the number of colors to infinity. So in that limit, if we were to do it by Feynman diagrams, all the diagrams would be planar, as the TÜV showed a long time ago. And because they're all planar, the important kinematic variables are the ones that are adjacent in an ordering around the outside. So not all of the kinematic variables are equally important. The important ones are the Mandelstam variables that involve a certain number of color adjacent lines only. Like S12 is important, but S13 is not an important variable. You can never get a branch cut in S13. You try to draw a discontinuity through this diagram, you can chop off S12 and S123, but not S13. And there won't be any poles in that variable either. So there are these distinguished variables, which we can always think of as differences of some dual or sector variables associated with these wedges. So we introduce these x's that live in the wedges between the external momenta. Now, what's quite amazing is that planar n equals 4 has a new symmetry with 4 generators in them, which are the special conformal transformations acting on these dual or sector variables. If you know ordinary conformal field theory, pretend that these are positions of points, that they're dual to that, but they obey the same symmetries, and you can generate the special conformal transformations by a combination of an inversion and a translation and another inversion. So the real key to demonstrating invariance of some function under the symmetry is that it should be invariant under inverting these x's. And it's a simple exercise to see that if this is the formula for how a single x transforms, the invariant transforms by picking up a factor of xi squared, xj squared in the denominator.
How was it shown? I mean, how do you prove that it's planar n equals 4?
Yeah, so it sort of comes from ADS CFT correspondence. And Alday and Maldacena considered the scattering of gluons at strong coupling using the ADS CFT correspondence. And they argued that the gluons are states of strings, but they live on a certain boundary of the ADS. In the intermediate states, the string world sheet can stretch into the bulk. It's pinned to the boundary when the strings come in. And as if you know about the ADS CFT, you may know that and we heard Tuesday about the symmetry group for the conformal theory in 4 dimensions is SO4,2. And that's also the isometry of the anti-de Sitter space. But then Alday and Maldacena applied a symmetry of string theory, which is T-duality. And T-duality, it kind of is a symmetry on the world sheet that exchanges the role of the world sheet time parameter, which propagates string states forward in time, and the sigma parameter that extends along the string. And normally when you have a string moving along, it has a momentum that multiplies this tau parameter, so that the tau derivative is the momentum. And there's also oscillators that wiggle it around there. But when you apply this T-duality symmetry, in the T-dual picture, the string becomes stretched in sigma instead of tau. And that sigma is the parameter along the string. So the string is now stretched out along a light-like vector for this massive gluon state that it's representing. And so now the thing you're supposed to compute, at least in the strong coupling limit in which the area of the world sheet is very large, so the fluctuations aren't important, is the minimal area for a surface that can go into the bulk of ADS. But on the boundary, it's constrained to match this boundary condition, which is a straight light-like line. So this is the prescription Alda and Maldacena gave. Is a nice picture by Amit Sever. And these, for n-gluon scattering, there would be a polygon with n sides, all light-like, at the boundary that closes. And the closure is momentum conservation. The sum of all the k's is equal to 0. So that's the strong coupling picture. So once this paper came out, people tried to check whether a similar picture was true in weak coupling. So this boundary would not produce a string world sheet, but it would be a source for coupling gluons to it. It would be a Wilson loop, a path-ordered exponential around this polygonal boundary. So there were a large number of calculations checking this picture of weak coupling. And up to certain divergent issues that can be dealt with, it was found that these, whenever you could work out the scattering amplitude here, it always coincided with a Wilson loop calculation on the other side, a weak coupling as well. So this symmetry is really exact enough to guarantee this equivalence up to some regulation issues.
This is true also at any loop order?
Yeah, this seems to be true at any loop order. So over here, we would calculate Feynman diagrams of a certain loop order by having gluons coupling in, but the external guys, gluons or their super partners, would go off to infinity. Over here, we also have gluons coupling in. At the first order, the gluon is doesn't know kind of what theory it's in. But at the next order, it can produce these gluino loops and scalar loops and so on, the full n equals 4 content. There's a more general version of it, to super Wilson loops that cover more than just bosonic Wilson loops. Technically, the bosonic Wilson loops are dual to the amplitudes that have 2 negative helicities. In the cases with more negative helicities, you need to kind of decorate these Wilson loops with other operators.
Sure, that's when you say decorated Wilson loop is other operators you mean at the cusps or
Well,
actually integrated along the lifelike sequence?
I think they, I have to remember it. They sort of sit at the cusps, I think, but I'm not 100%. I have to check that. So this Wilson loop is defined with these corners that are in like a, they come from this dual space, and there's a symmetry of it under this inversion that's inherited from the string picture. And what that means is that the answer can't be an arbitrary function of these xij squareds. To have that symmetry, we do the same thing that's done in ordinary conformal field theory and position space. We form cross ratios. And you can check that this cross ratio is invariant under this symmetry, because the numerator will go back into itself, but there will be a factor of xi squared, xj squared, xk squared, and xl squared in the denominator. But then the denominator will put exactly those same factors in the numerator, because all we've done is switch the order of J and K there.
This is also invariant under translations. Or
Well, we did translations is just the statement it's made out of XIJs.
Mhm.
There's also dilatation, and that's also, once you make it conformally invariant, it's dilatation invariant as a byproduct. Now, in contrast to normal position space conformal field theory, the difference between two adjacent xi and xi plus 1 is this massless momentum or light-like vector. So we don't have the same number of variables as you have in the position space case. In fact, for 4 external gluons, you might try to write down x12 squared, x34 squared over the other guy, but those numerators are 0, so you actually don't have any cross ratios. And you don't even have any in the 5-point case. But in the 6-point case, you can start to build these cross ratios. So basically, you're not allowed to use the edges of the n-gluon because those are light-like. But I can kind of draw a little box in here, which I put in the solid line, the numerator guy, x13 and x46. And in the denominator, I draw it with dashed. As long as I have a dash and a solid coming into the same line, then it cancels off this invariance. And just to remind you, if you're more comfortable with Mandelstam variables, this would be a couple of 2-particle Mandelstam variables in the numerator and a couple of 3-particle ones in the denominator. So that's one of them. And then the other ones are obtained by symmetry. We just cycle around using the cyclic symmetry of this hexagon. We can make 2 more of these. By the time we cycle 3 times, it happens that we come back to the original variable. So there are 3 of these kinematic variables. And you can understand that if you remember the normal 6-point process, 2 goes to 4. There's like, you might have thought there were 9 variables if you counted Mandelstams, but there's really only 8 because of a Graham determinant constraint. But we have 5 more symmetry generators. We have the dual conformal and also dilatation. And 8 minus 5 gives us 3. So it's always 5 fewer than sort of the generic situation. And every time you add another particle, you get 3 more variables. So if we were to go to the 7-point case, we'd have six of these variables and so on. So that's sort of the kinematic playground. This is sort of a dream of what you could do, what we would like to do eventually. I mentioned that at strong coupling, there's a prescription from string theory for calculating amplitudes. Way up here at very strong coupling, we find the area of a minimal surface. There's actually some very interesting ways to use integrability explicitly there to solve this problem. I'm not going to say much more about it. But there's other regions that I'll say a little bit more about later, where there's an expansion called the flux tube expansion. And that is in a kinematic variable. And it's sort of a series of terms that are ordered one after the other, very similar to perturbation theory. So there's really like a whole set of vertical lines where we have some control over what's going on at any order in the coupling. And then I'll tell you about this amplitude bootstrap, which constructs perturbative expansions around 0 coupling. And every time these sets of lines here and these sets of lines here intersect, we get data we can either use or cross-check that both frameworks are consistent with each other. But eventually, we would like to do arbitrary kinematics for arbitrary coupling. That's sort of the holy grail, or the castle in the sky or something. That's the goal eventually.
Lance,
Yeah.
assumption is that evolving in lambda, it will be continuous downward phase transitions. Can you show it?
I can show in some cases that there are no phase transitions. I mean, in the cases where you can do these things with finite coupling, there aren't really any evidence of any phase transitions. Things seem to move smoothly as gluons kind of evolve into strings. So in terms of what the arenas that we've been looking at so far, I showed you the six-gluon case where we could get to 7 loops and pure gluon, pure partonic amplitudes with 7 of them through 4 loops. But in these cases, there's still this difference in the number of kinematic variables in planar n equals 4 than in QCD due to the dual conformal symmetry, these 4 special conformal generators. I mean, QCD perturbatively sort of has scale symmetry, so it's don't really count that as being different. So what I want to do then is to switch to a new arena, which we've been working on for a shorter amount of time, which is actually simpler. It has only 2 variables instead of 3, so it's a little easier to describe. And also the dual conformal invariance is sort of broken in a way. So the QCD and planar n equals 4, at least the kinematics are even more closely related. And we can go one more loop order to 8 loops because it's simpler. So this is an analog of something that's quite studied in QCD, which is the production of the Higgs boson at the LHC. And the production is done through gluon fusion. And here I've given an example 8-loop graph plus a 9th for the top quark of 2 gluons coming in and producing a Higgs and 1 recoiling gluon, just as an example. So if the Higgs mass were sort of arbitrary with respect to the top quark mass, we would need to do this loop integral with massive lines in it, which is quite different from these massless guys. We'd need to do that explicitly. But in fact, the Higgs mass is only 125 GeV, and the top mass, or more importantly, twice the top mass, which is when you first hit a cut in that channel from the top, is quite a bit bigger at 350 GeV. So it turns out to be an excellent approximation to integrate out the top quark and replace its effects by the leading operator, which involves the sort of the QCD Lagrangian multiplied by the Higgs field with a 1 over V. If you want, you can do higher order corrections that have higher dimension operators here, either more fields or more derivatives, and get more terms than 1 over m top. So we're not going to do this literally. We're going to do the n equals 4 analog of this. So
in that example, it wasn't a 3-gluon in the end, the operator you wrote down. Unless I'm
sorry, yeah. So the operator produces 3 gluons, and then you can take matrix elements of that operator with as many gluons as you like. In the leading order production, you only have 2 gluons, so 2 incoming gluons that fuse to the Higgs. But part of the problem when you compute to higher orders in the coupling is that the next order you immediately radiate 1 gluon. So you get stuff like this, although just at tree level. So this 8-loop guy would come in at end of the 9th LO production cross section. So a few loops past what we are actually at right now, which is N3 LO. So in this theory, the bootstrapping is very efficient. So with Andrew McLeod and Matthias Wilhelm, in December, we were able to push the state of the art from the previous 2 loops to 5 loops. And now we have a paper we're finishing up, which goes to 8 loops. So now the new standard is 3 loops at a time, which will cut down on journal proliferation. So this Higgs is a scalar particle, and it's a color singlet. So basically, it injects momentum into the 2-gluon state. And so we can call it a form factor or a matrix element of an off-shell operator, this operator, with on-shell gluons, the guys over here. Now, in n equals 4, there's a whole super multiplet of operators that basically their matrix elements all behave almost exactly the same way, up to some of these factors from Susie Ward identities. And this operator belongs to a chiral and VPS protected, so it doesn't have an anomalous dimension in n equals 4, whereas it does in QCD. BPS protected stress tensor supermultiplet. And there you could choose other operators in that multiplet if you want. For example, there are those scalars. And if you choose some kind of traceless piece of it, that will also be in the same multiplet, this biscalar operator. Now you might ask, why didn't we, and you sort of did ask, why didn't we look at the 2-gluon form factor? Well, it's just too simple kinematically. Same reason we looked at the 6-gluon amplitude, the 4 and 5 ones were kind of totally constrained. And in this case, it's even more obvious. There's only one kinematic scale for 2 gluons. It could be carried, these loop amplitudes carry some epsilonic dimension, but beyond that, you just get numbers. And to bootstrap something, you got to have a function of some non-trivial dimensionless ratio. The one we're going to look at, which I just call for slang HGGG, although it's not really the Higgs, that has 2 dimensionless ratios. And so we can explore the kinematic space that it lives in. This is actually the kinematic space here. So there's the Higgs has a mass m Higgs squared. But by momentum conservation, that's also the square of the sum of the 3 gluon momenta, which is often called S123. But it can also be written by expanding out the dot products and using the ki squared to 0 in terms of the 2-particle invariance. And so you have what's sort of a Dalitz plot here, this triangle. I show U and V. But if I take and divide this by S123, you see that 1 is equal to U plus V plus W, which are defined by these. These are ordinary ratios, not cross ratios, because there's only one S in the numerator and one in the denominator. And this is sort of a Dalitz plot for the decay of a massive particle into 3 massless particles. And this is a Euclidean region where all these invariants are positive. But there are other regions where some of them are negative, and they're related by symmetry. So this region 2A is one where the so-called Higgs is space-like, and 3A is where it's time-like. Anyway, we can work out the amplitudes in any of these regions. This n equals 4 amplitude is actually S3 invariant under a symmetry, which has a cyclic permutation of U, V, and W, rotating this triangle around, flip it over. So these other amplitudes, they're in bigger spaces, which are harder to picture. At least this one, you can see the whole thing on a slide. Any questions about that?
So just a general question.
Yeah.
You are now using a method that requires kinematical variables, so it will not work for a 4-gluon amplitude.
For the 4
For a
gluon?
4-gluon amplitude.
Yeah, the 4-gluon amplitude, because of this dual conformal symmetry, I mean, it has kind of an anomaly, but it's basically fixed to be, the kinematic dependence is completely fixed in just terms of numbers at each loop order.
So how would one compute that amplitude?
That's a tricky question. And even when I have the 6-gluon amplitude I tell you about, I've actually divided out something which is closely related, which is basically that like that 4-gluon amplitude. So I don't know some of the divergent constants that I'm supposed to know in order to combine it with everything else. I know them up to 3 or 4 loops because they've been computed that far. But we know the finite parts to 7 loops, and we don't even know the divergent parts to 3 or to 4 loops, all of them, or 5 loops. Yeah, so no, it's a good question. It's in some kind of a regularization scheme, but trying to connect it back to something people usually use like dim reg is there's a little bit of a stumbling block there.
So just to be sure, that's you're talking about IR divergences.
In this case, I'm talking about IR divergences on the amplitude side, and they're dual on the they're UV on the Wilson loop side. I'll actually say something about them in a couple of slides. So just as an example, in one loop, you get, I showed this integral before, and here I'm just rewriting it. So you see what it looks like in terms of U and V. So it has log squareds involving U and V, and then these dialogues with these arguments in it. And at 2 loops, I'm not going to show you exactly what it looks like in general, but it was computed in QCD back 10 years ago, probably unofficially earlier. They put it out then. And then soon after that, Branduber, Charliini, and Young did this analog calculation in n=4 super Yang mills, planar. And they saw something kind of cool, which is that if you just took the highest weight part of the QCD amplitude, remember I said that they go up to weight 2L? So then you go and you also have to set the CF to CA, the Casimir. It was exactly the same as the n=4 result. Actually, there are a couple different helicity configurations and some little prefactors, but the bulk of this transcendental function was exactly the same. That's something that happens in various places, but it's a stronger statement than what I made before, and it doesn't happen everywhere. It was observed before in the anomalous dimensions that control parton splitting in QCD, Altarelli Parisi or DGLAP, and also a similar one for small x physics. So they obey this sort of transcendentality principle. And this is maybe the most complicated place where it seems to work in terms of having 2 variables, whereas the other ones are sort of 1 variable things. So now I'm going to just show you how you can define the function space that German and Ramidi put these answers into. They wrote them as specific integrals. I'm just going to define them differentially instead. So the derivative with respect to u is something over u, which is another function in the space, but 1 weight lower. And then there's also a similar one with w, and this is actually just w. And then similar ones with 1 minus u and u plus 1 minus w over here. So this is sort of a system defining a tower of different functions iteratively. Once you know how to enumerate them at 1 weight, you can lift them to the next weight up. And so the strategy is to find a subspace of the spaces defined by these systems and to construct it to as high a weight as possible in order to find this form factor inside it. And it's similar strategy for these other 6 and 7 gluon amplitudes and stuff. And a little more general way of phrasing what this space is. This is one example of a class of integrals called generalized polylogarithms, which were sort of known in various guises to mathematicians for a long time. They're sometimes called G functions. So in general, you just keep integrating lower weight G functions with a D log. So dt over t minus some a, and you put that in front. And there's a kind of related definition, which is closer to what I showed you on the last slide, where you write the general differential of a function of weight n as sums of functions of 1 lower weight times d logs of some class of objects called symbol letters. And in the previous example, there were 6 letters in the symbol alphabet. There is a more fancy mathematical object called a Hop algebra that allows you to pick apart these polylogs and turn functions into sums over pairs of functions. This is just one piece of it, where we map functions to lower weight functions in the space times sync logarithms, which are weight 1 functions in the space. So this is the n-1, piece of a coaction operator called delta. So we call this the n-1, coproduct sometimes. And these are letters in the symbol alphabet. And this covers a lot of different computations that have been done in perturbative QCD and n=4. And you just, when somebody says this, you ask them, well, how big is your symbol alphabet? And if it's 178, you say, oh, you're going to need a lot of computer power. So we just have 6.
I apologize, you probably
No problem.
said, I just missed it. What did HPL on the previous slide say?
Oh, sorry. HPL is another definition. That was the terminology that they gave to it. They called them 2D HPLs. Because in the physics community, people doing the splitting amplitudes invented harmonic sums. And then in X space, they were harmonic polylogarithms. And then those were just one variable. And then they were promoted to, I mean, Remedi and Vermazerin invented these harmonic polylogs. And then they needed 2D versions, and that's what they called them. So they're a special case of these more general G functions. Yep.
I have a question. So this grid structure, I mean, you have a way to determine what happens if, for instance, you introduce 1/n corrections to the large n, or I don't know, you break softly the supersymmetry by adding some masses to the.
Yeah. Well, we haven't explored that very much. I mean, people have looked at the subleading and 1/n corrections at 2 loops, and in a couple of cases at 3 loops. And well, things look different because the variables are different. You now need to use all the non-dual conformal variables to express things. And you can also add masses. External masses are like operators in some, but if the particles have mass, everything becomes more complicated. QCD has the nasty habit of containing the top quark, and the top quark runs around in loops and has a mass comparable to the scales of the process. And those integrals tend to be more elliptic. Elliptic integrals are outside of this class. This is a special class where we can push things very far. There's a whole set of things, even if you go to more complicated kinematics, even if you don't go to 1/n corrections, even if you don't add masses. So yeah, it's a big story. We're just trying to do the simplest case first. So in this polylogarithmic context, though, we can iterate things, and we can keep taking derivatives of the n-1, 1 coproducts. And then we get these guys, which are also called double coproducts. And then we keep going all the way down. If we start at weight n, we can do this n times. And then we'll get objects which are sort of coefficients of all these d logs. And you might have heard of something called the symbol. I heard Anastasia Volovich gave a talk here at some point. And she was also just probably talking about symbol alphabets. And they kind of brought the symbol to the physics community about 10 years ago. And the symbol is often abbreviated by, instead of writing the logs all the time, you just write your arguments over here. And so you get an n tensor product of terms, and these things are just rational numbers for a given coefficient, but there's a big array of them. And that makes up the symbol. And the symbol loses information about constants because you've differentiated all the way down. And it kind of loses information about which way you go around branch cuts. But it's a nice scaffold for the answer. And usually if you can get the symbol, you can go back and get the rest of the answer later. So the symbol alphabet for this system, if you just look at these things and recognize that they're all d logs of exactly the argument I put up there, you see that the symbol alphabet has these 6 letters, U, V, W, 1 minus U, 1 minus V, 1 minus W. So every derivative is a sum of at most 6 guys. In fact, it's only 4 for U and V derivatives. And if you want an exercise, I told you about this thing here. You can take its derivative and check that it's inside this space. Just for comparison, I'm not going to go through anything explicit for the 6-gluon case, except show you some results. For the 6-gluon case, the alphabet is enlarged to have 9 letters. Coincidentally, 6 of them look like the ones for the form factor, but there are 3 more, a little more complicated ones. The n = 7 one has 42 separate letters. And that's kind of the boundary of what you can do to computationally at the moment to higher orders. And n = 8, there's at least 222 letters that have been found recently at 3 loops. We don't even know if that stops when you go to higher loops. In these cases, it looks like the number of letters stabilizes. So we can use the same alphabet to arbitrary loop order. But we don't know about the n equals 8 case as much. And once you're sort of given this alphabet, you can actually try to construct all of the functions in this space to some high order. And the idea is to use that differential definition to define the functions at one weight higher. Naively, if you had dn minus 1 at one weight lower, then at the next weight, you might think you would get 6 of them, 6 times as many, because each derivative would have 6 of these terms. But in fact, there's an integrability constraint whenever you have more than one variable. And this, it's not automatic in how you would construct this. So it's a lot less than 6 times as much. It's actually 3 times as much once you impose these conditions. So these conditions, if you plug through the definition of the derivative, they turn into constraints on the adjacent, on these double coproducts. And so then you just go and impose these constraints as linear constraints, and you can define the functions this way to higher weight. But in fact, we found more empirical constraints on this space that we use to trim its size down even more. So roughly speaking, it looks like this. It kind of grows at a fixed rate in dimension, and the low-lying guys are identifiable functions. Like these are just single logarithms in these 3 variables. There's actually no log of 1 minus u. That's a branch cut condition. And then you get dilogs, double logs, and then you get higher ones and these true 2D HPLs and a bunch more higher iterated integrals. Then you just go look in there for the right answer. And it turns out that there's a change of alphabet you can do that exposes some grammar or some nice rules for combining the letters. Like when you write it in this change of variables, the symbol at 1 and 2 loops become extremely simple, just a couple of terms. And there are a huge number of adjacency constraints in terms of these letters. These guys we found also hold for 2-loop QCD amplitudes for some reason, both planar and non-planar. But then there's an extra batch, which we've now verified hold through 8 loops in the planar n equals 4 case. So there's some dihedral symmetry and mnemonic for which ones vanish. But anyway, I didn't even really say yet what the boundary conditions are that we use, but I hinted at it that there is a kinematic limit in which the answers are known or proposed at finite coupling. And they involve a flux tube picture that was developed by Basso, Sever, and Vieira. But for our purposes, there's a cookbook recipe that we can plug into to understand what happens whenever the amplitudes have 2 gluons that are near the collinear limit. And this wasn't available. And those are these closed hexagons and so on. But recently, these guys, Ahmed Sever, Alexander Tumanoff, and Matthias Wilhelm, they figured out how to deal with Wilson loops that are only not strictly closed, but shift by a certain amount. And this shift is necessary because the operator injects momentum there. So this is the kind of Wilson loop that's dual to a form factor, whereas a closed Wilson loop is dual to the to a n-gluon amplitude. Anyway, they constructed this ingredient and they were able to give us predictions that we could use to fix the amplitude in the full kinematic range. As I was mentioning, there are these divergences. In view of the time, I'm not going to go into it anymore, but we have a way of dividing them out and getting a leftover thing, which is finite and dual conformally invariant, called the remainder function. There's also another quantity which has even better structural properties which is just sort of a directly normalized amplitude. And there's this one of these for all three of these systems I was talking about, 6 and 7 gluons and the form factor. So they all behave very similarly. This is the table of parameters that we have left as we construct an ansatz. So like a for loop, say, there would be 1,290 parameters in our ansatz, because that's the number of weight 8 functions in the space we've settled on. And we use dihedral symmetry, which has like 6 elements in it. So it reduces things by roughly a factor of 6. And then we have some other constraints, which are partly empirical, but they reduce things by another factor of 10. We have another not empirical constraint. We have this collinear limit. And at this point, we reach into this dynamical OPE data, but we hardly need it at first. We just start to need it more and more at 7 loops, and then we hardly need it again at 8 loops for some reason. So this is basically how it goes. You impose these linear equations, and over 8 loops, you have tens or hundreds of thousands of equations to solve, but it can all be done.
Sorry, Lance.
Yep.
What is T in this dynamical OPE?
This T?
Yeah.
V is T squared.
Oh, okay.
Sorry, this is the parameter that's used by the OPE guys.
Mhm.
And T, the number of powers of T counts the number of flux tube excitations. And in the hexagon or heptagon, you need just one, but here they have to come 2 at a time, it turns out. And that's why there's the T squared. Then there are some logarithms from expanding the energy perturbatively that decorate things. Anyway, I'm going to skip through this and just show you a couple numerics on 2 regions. One is a line through the Euclidean region, it's like decay. And one is a Reggie limit, high energy limit. So this is the ratio of successive loop orders. So like this last line is the 8 loop answer divided by the 7 loop answer. And you'll see as the loop order goes up, these curves get flatter and flatter. It's kind of amazing how flat they're getting. Why are they getting so flat? Well, one clue is provided by looking at what that number is. We have a secret parameter called the cusp anomalous dimension, which plays a huge role in these things. And we know it to arbitrary loop order. So we can evaluate the ratio of the L loop to the L minus 1 loop. And we find that it's within 3% of the value at this symmetric point here. So the suggestion is that this is telling us that the amplitudes in this theory have the same large order perturbative behavior as the cusp. And it corresponds to having a finite radius of convergence. So a finite radius convergence means that the ratio should eventually be identical. And we think it should be -16. And that's what it is for the cusp. But we only got to 8 loops. So it takes a little while to get to -16. So we compare it to the cusp because it's just as defective as its quantity. Anyway, this fact that everything spreads out and becomes flat says that unless some other physics is going on, like some large logarithms near a boundary, basically in the bulk kinematics, it looks like grows at the same rate as the cusp roughly. And then we can also go into these high energy or Reggie limits. In this case, we normalize a little bit differently. So this is really actually a space-like Higgs, but it's an interesting thing that we call an impact factor in the Reggie business. In this case, we've collapsed onto one-dimensional lines. So the answers can be written as these one-dimensional functions, which are often called HPLs. They're very similar to these G functions. And they just have binary codes for whether you use how you differentiated, and then an integer in front. So it'd be really cool to figure out what all those integers are. So we need some machine learning expert to tell us how to decipher the thousands of integers we're generating and tell us what the ninth loop order is, so we don't have to do the same strategy we did before. So, well, we are playing around a little with machine learning, but nothing to report. This is the six-gluon kinematics. It's three-dimensional, a little more complicated. I'm just going to show you one line and one point in this space. The point will be at the origin, that target there. The line will be that red line. On the red line, we plotted another quantity called the next or non-MHV amplitude, and we see the same kind of behavior showing up. Here's this -16 target. Again, you see everything's flattening out in the bulk again. So it's not like we just have one place where this happens. We go to random places and very similar things happen. And I think I'm just going to skip this in view of the time, but anybody who wants to stick around for more punishment, I can describe the origin. But you did ask about phase transitions in the coupling. So this is a piece of the answer at the origin, Kobe. And these are finite coupling evaluations. And everything's very smooth. It goes from perturbatively going like g squared, and divided by g, well, looks linear, to something that goes like flatten g or multiply that, square root of lambda. But anyway, I'm glad I got the chance to tell you about this program of trying to build up very high loop order results for various scattering amplitudes and related quantities. And in some cases, we can go beyond perturbation theory to finite coupling with various assumptions. What would really be great is to do it for generic kinematics, and then maybe we could say that this theory had been solved. And of course, going away from the supersymmetric case to non-planar cases, those are important open problems which are harder, but definitely deserve attention as well. So thanks a lot for your attention.
I just ask, so you use like you invoke like the mass of the Higgs and the mass of the top and things like this, which are very physical, real world quantities to talk about a particular amplitude. But is it, maybe this is just the last line on there, but is it obvious what kind of lessons I should be taking about this for like a physical amplitude that would actually be?
Well, as an example, we have a guy at SLAC, Bernard Misselberger, who calculated the Higgs production cross-section at N3LO. At N3LO, he needed the two-loop piece. At some stage, he'd like to go to N4LO. Now he needs that same 3-gluon amplitude at 3 loops. And there's a algorithmic way to set these things up, but it's computationally very intensive. And one of the hardest parts is figuring out what the differential equations are that the key master integrals obey. So, if we have a clue, give him a clue, he can test it out. And if it's a simplified structure, it's much easier to verify that it's true for all of his integrals, which include the ones we have, but more. So it's not guaranteed, but I think this is an example of how you can take information from this n=4 world and have it help out in things that are at or beyond the state of the art in QCD. There's also other things, this maximal transcendentality principle. It often enters quantities like anomalous dimensions that play a role in resummation. So it might be possible to push the connection further, at least for pieces of quantities that you want to resum. Some of the resummation involves Wilson lines, even in QCD, which are semi-infinite, and represent the direction of asymptotic particles. When you have to couple a bunch of those Wilson lines together, the first time you get that kind of color structure, it only involves coupling them together with gluons. And because it's just gluons, it's the same thing in both theories. So you already kind of know what to expect from this transcendentality principle. So there are some other ways to connect it more to the real world. I didn't go through completely.
Can I ask one other question?
Sure.
And then Massimo can. But so you talked about doing these computations, and one of the things that you were using were empirical. I can't remember the phrase used, but it was an empirical relationship that allows you to reduce the.
Yeah, like one of them is which letters can appear next to which other letters. Or
Yeah,
the
so-
grammar of the alphabet.
Yeah. So how do I think about that? Because it's in. Do you know it's true, or you've just seen it enough that you believe that it's true, or?
I would like to say the latter, except there are some cases where we found some empirical relations which held through 6 loops and bombed at 7 loops. So the brain has a chance to see patterns that aren't exactly their tall orders too. So you have to be a little careful. But the ones I mentioned, they are simple enough that you can see them early on at 3 loops, and then you see them for 5 consecutive loops, and you become a complete believer. But some of the ones,
So far, so good. So far, so good.
so far, so yeah.
So it's so that you had some target values for your integrals that were conformal dimensions, but why are you expect those integrals to eventually go to conformal dimensions? Is there, let's say, a strong coupling string?
Well, we don't really know for sure. It's just kind of a smoothness assumption that everything behaves the same way unless it has a good reason not to.
So, but in the strong coupling limit, those integrals will be equal to the first dimensions. If you go to large top.
Well, you know, saying that something has the same radius of convergence doesn't actually mean that its value is the same. It's a less powerful statement. So we saw some case, one case I showed you at the very beginning, where the strong coupling shape was extremely similar. We don't know why that works so well. That's kind of a stronger statement than just that the radius of convergence doesn't seem to depend too much on the kinematics. This is a pretty empirical science. We just compute things and look at them and try to compute more if we find patterns. And if it works and all the constraints are satisfied, then we can collect more data.
Here, when you wanted to extend to QCD, where is the running? I mean, where do you see the running?
Well, you would see it because like at one loop, you would see it in the bubble integrals. Those are UV divergent. Whereas the boxes have no UV divergence at all. They have a canonical set of infrared divergences. And the same would be true at higher loops. There would be topologies that would have sub-bubbles. And they would also have primitive divergences at 2 loops that aren't bubbles, but they are maybe 2 triangles glued together inside the graph. So you would see all those things at the graphical level. And some of those functions, you know, could be consistent with this function space I was describing. We actually know that this function space, which covers all 2-loop QCD integrals, is not the right function space for QCD to arbitrary loop orders. It actually contains in it a special class of integrals called propagator integrals, or 2-point functions. And people have studied all the generic Feynman integrals of that type, and they become non-polylogarithmic type at 7 or 8 loops. But it's still conceivable that we could get a lot of the 3-loop stuff needed for QCD out of it. Glennis had her hand up a while ago.
I was curious, it's a real off-the-wall question, if you can see any way of relating this to an attempt to prove confinement.
Yeah, I haven't thought about that much. It's a conformal theory, so first you gotta break the symmetry and work on that case. I mean, I think I don't know the whole story, but confinement definitely happens in n=1 super Yang mills, and my impression was it might be understood a bit better there than in QCD, thanks to holomorphicity. But I don't remember, you know, how rigorous the arguments are in n=1. So that's where I would try to use supersymmetry to prove confinement, I think. You have a question?
So I just want to follow up this question. So I mean, the goal of this program is eventually to understand better n-mean theory, pure n-means. But it seems that the framework is very different. The physics here goes smooth from strong to weak, whereas
Yeah, well,
gluons
sometimes
are
you
very
say you
different
have a
than
goal in the
gluons.
beginning.
So maybe I just think
Yeah.
maybe this program is doomed to fail, and you will do this 800 loops.
We
and
don't say
eventually you learn
fail.
nothing about
We don't say fail anymore. We say pivot.
You're from Silicon Valley, right?
Yeah. I know how to pivot. So, the farther you go in the loop expansion, the more different n equals 4 looks like than QCD. At one loop, we found it extremely useful because we could literally write the gluon amplitudes. We could split the gluons and fermions running around the loop, and we would also put some scalars around the loop. So that's 3 things. So we would trade them for n equals 4, n equals 1, and scalar. And then the scalar had some virtues that the gluon was more complicated. But the extra bit was actually supersymmetric. And so once you organize it that way, it's the way the amplitude wanted to be organized in terms of the analytic structure. So, so we learned some things, but the farther you go in the loop expansion, you still only have 3 things you can dial, and you have more and more things to try to disentangle. So it gets further away. So then it's not so much a literal decomposition of the amplitude. It's more of a statement about understanding the function spaces that you need. And this is some partial work in that direction. But there are many other more complicated function spaces that you won't understand for different QCD problems through this route exactly. I mean, there are techniques for dealing with them. We do like technical things, like how do you plot these functions? They're just so massively complicated. They have massively complicated functions in QCD also, and the strategies are similar. You use the differential relations to get everything out. You do a series expansion in one direction by using the differential equation. And then you establish a beachhead here where you know the values and all the derivatives, and then you go over here and stuff. And in some ways, this is a smarter way of doing it than naming a function a polylogarithm. Because at the end of the day, to get numbers out, that polylogarithm is an instruction to do all of these integrals. Probably be faster just to, I'm not actually saying that we told QCD people that because they understood it independently.
Yeah, so if you go to the real case, you say we can just integrate the top part, but I'm kind of confused. It seems the error of just the keeping the lowest order of the EFT is even larger than the higher loop.
Yeah, I think well, you can treat the higher order operators in a very similar way. I mean, mathematically, the contributions of the higher order operators should involve all the same functions as before, because you're kind of doing the same loop integral, but you might have some more derivatives in the numerators. But the derivatives in the numerators don't change the essential functional form. In practice, people haven't done it as high order because it's smaller. And it was much more important to get the first couple of orders of perturbation theory in alpha S than it was to get the first 1/n² corrections for the Higgs total cross section. If you start producing the Higgs with moderately large transverse momentum, then you have to, this thing quickly breaks down, and you may have to actually do the top loop as well. So people work on that as well. But
it seems if we do a naive dimension analysis, the higher dimensional is like an image over at top kind of to some power, but so this is kind of comparable with like full pi.
Yeah, it's usually, well, at least the low orders, it goes from dimension 4 to dimension 6. So it's the square. It's actually the square of the ratio. So it's more like a 1/9 or something. And the alpha S is not really the right size of the corrections. They're usually bigger than alpha S over pi times pi. They're bigger than that. Yeah. So Yeah, even at the, even like it's amazing that the effective, the 1 over m top corrections are pretty small usually.
Professor Dixon will give a colloquium tomorrow and also talk at a meeting CCNY.
That's right.
Is that on Friday?
ITS. No, that's next. That's a Zoom talk. I believe that's in a couple of weeks, like November 4th.
Oh, yeah.
Or that week. I forgot the exact date.